2946. So we have a loop of this shape with a current I, which is given 5 amps. And the loop consists of two semicircles of radii R1 and R2. Those are given, right? 1 centimeters, 2 centimeters. Of course, at some point you'll have to convert them to meters. And then there are two horizontal pieces of wires connecting these two semicircles. Of course, since there's a current, whenever you have a current, there are moving charges, there must be magnetic field. Of course, this construction is going to create magnetic field everywhere. The whole space will be filled with a magnetic field. And the problem asks, what about the net magnetic field, the total magnetic field at this point P, which is basically the center of this semicircle and that semicircle? Of course, the problem could have asked about magnetic field at any other point, but I'm telling you, if somebody asks you to find magnetic field, for example, at this point or that point, it's a clear indication that that person just hates you, right? So, and that person wants you to suffer, right? Because it will be really, really complicated integration. But finding magnetic field at this point P will be reasonably easy, because we have nice symmetrical problem is nice and symmetrical relative to that point, right? But still, nevertheless, it's significantly more complicated than that, and it will take us some time to handle this. In your homework, you're going to have a slightly different situation. So first of all, you're not going to have this angle 180 degrees. So it will be a smaller section. I don't remember, like 60 degrees, right? Then this semicircle is going to have infinite radius. Pretty much this semicircle will just disappear. So you're going to have this part of the circle with angle subtended by angle 60 degrees, and there will be this section, and that section will be here. So approach that you will have to apply will be very similar to what we're going to do now. But of course, configuration is slightly different, and I think that problem will be easier, somewhat easier. Right. Because in that problem, you will not have to you will not have to find magnetic field created by this outer semicircle. Okay. Anyway, so let's see what can be done. First of all, in terms of which expression can be used, can we use this? No way, because that is only correct. It's a magnetic field created by an infinitely long straight wire. We don't have infinitely long straight wires. Yeah, we have small straight sections, but they're not infinitely long. So we cannot use that formula. It will be illegal, right? And of course, we have semicircles. So pretty much it means that this cannot be used. So then what can be used? Biot-Savart law. Biot-Savart law doesn't have any restrictions. It can be applied to find magnetic field created by any wire. You remember I showed you something. Even for you can use that to find magnetic field created by this strange piece of wire, right? But in our case, we have this situation. So Biot-Savart law we'll have to use. Can be abbreviated as BS law. No, it's correct. Biot-Savart law, BS law. Right? So okay, you know what? Let me write. So BS law, and we're going to use. And you see, I'm writing dB because I don't like author use just B. It should be dB. All right, and mu naught divided by 4 pi, and then current, and then the cross product between ds, r hat, and r squared. So that's what we will have to use, right, in this problem. And of course, we will have to integrate, because that is the contribution to the net magnetic field created by small section ds. So we'll have to do integration. Integration is an additive thing. So you can split it into as many integrals as you want, right? Or if as you need. In this case, we will have to integrate over the whole loop. And I think it's obvious, logical to split this loop into 4 pieces, 4 sections, right? So the first one, this semicircle, for example, right? Let me label it sort of like 1. So that's the first section. And also let me label this corner as point A. This, I think I labeled this, wait, let me check. Yeah, this will be my B, this will be my C, and this corner, let me label it as D. So obviously we can split into 4 sections. Semicircle from A to B. Then that semicircle from C to D, let me label it as 2. And then 2 these horizontal pieces. I think I labeled this as 3. Let me check. No, this as 3. So this will be my section 3, and this will be my section 4, right? And so, of course, finding the net magnetic field created by these 4 pieces separately will be much easier, right? So, as a result, in order to find the net magnetic field at point P, we need to find magnetic fields created by these 4 sections separately, right? Okay, so let me write that. So I can write B net equals to B1 plus B2 plus B3 and plus B4. So pretty much you see we're diving slowly deeper and deeper and deeper, right? So now we see that we need to take care of separately of each of these contributions, right? So now let me start with B1. I will put here a small bullet and I will write B1. And okay, let me check if I mentioned everything. Coordinate system. Yeah, also, I didn't say anything about this. You see, I introduced coordinate system also like over there, right? But this time z-axis is into the board. Because pretty much I can tell immediately what will be the direction of the net magnetic field. So I'm trying to make that magnetic field positive, right? And again, you remember you have constitutional freedom to choose or orient your coordinate system in any way you want. You will never be wrong, right? So I choose this coordinate system. Right? It's still right-handed, so it's good. Speaking about right-handed coordinate system, it's like watch a video of Walter Lewin from MIT. Now he's retired, right? In one of his sections, one of his lectures, he said, "You must use right-handed coordinate system. If you're going to use left-handed coordinate system, I will kill you," right? Because everything is written for the right-handed coordinate system. And if you start using this left-handed, you will start creating this unnecessary mess, right? Confusions, right? No. Right. So, right-handed, right? And so now let's take care of B1. And first of all, let me take care of the direction and then magnitude, right? You know what? Yeah. So section 1. And first let me write direction. Direction. Right. So you remember what when we discussed Biot-Savart law, I told you what determines direction of the magnetic field in the Biot-Savart law. It's this construction ds cross r hat. Let me even circle it slightly, right? So that's what determines direction, right? So in order to find direction of the magnetic field, so we need to look at that cross section. I mean cross product cross section. The end of the week, I started blabbing some nonsense. All right, so ds cross r hat. So that's what we need to analyze. And so in order to analyze it, of course, we need to see these vectors on the picture. And we are on the section number 1, so it's a B1. So we are on this semicircle. So let me draw ds and r hat. So ds, let me draw it here. So you know what? Let me move this slightly. So it will be No. You know what? I want to save that space for, okay, for analyzing R2. So let me draw ds over here. So that's my ds. Okay, I can even add subscript 1. You see why I changed the position? Because I want to analyze section 2 over using ds over here. So I need the space for the picture. And so I needed to shift ds1 slightly to that side. So that's ds1. Actually, I can even add the subscript over here, for example, ds1. Right? So it's tangent to the circle, semicircle. Then what is r hat? R hat, you remember we discussed, it's just a unit vector which shows the direction from what? Biot-Savart law. From the section ds to the point where we want to find magnetic field. All the time, this R hat from ds to the point in question. Right? So let's draw it. So first of all, R distance, again, from ds to the point in question. Damn it, it's ugly. Right. It's still ugly. Okay, doesn't matter. All right, so that's distance from ds to the point where we want to find magnetic field. And then our r hat, it's this. R hat. You see? Okay, hat can be made, we can make it bigger. Right. Again, from ds to the point P. Right? Okay, so now, in order to find direction, we need to apply right-hand rule number 1, right? So ds cross r. ds that way, so I have to align my hand like this. Okay, and orient it like this. So with my palm down, in that case, I can bend my fingers along r. R is down, right? So ds cross r, and my thumb, outstretched thumb, gives me direction of the magnetic field created by the first, by this section ds. So it will be into the board, into the board. Let me check if I got the correct direction. It should be, yeah, no, yeah, correct. So which is the positive z direction? So yeah, that's what I wanted. Which we wrote, I will just, instead of equal, I will just put like this and write into the board, into the board. So which is, it will be, and also look guys, this will be direction of dB1, right? But when you start integrating that dB1 in order to find the net contribution from this section to the net magnetic field, again, when ds is over here, r is still that way. So if you again take a cross product, still direction will be into the board. If you take section over here, here, it doesn't matter which section ds you will take on this semicircle, every time a direction will be into the board. So during the integration, directions are the same, so it means that our magnetic field B1, this B1, right, total contribution from this semicircle will be in the positive z direction, so it will be absolute value of B1 and in the positive z direction. Right. Okay, so now we know the direction. And you know what? I can actually draw it here. So B1 will be into the board B1. Okay. Now, what's next? A magnitude. Let's find magnitude of B1. We just found a direction. Now let's find magnitude. So now the second magnitude. And of course, now we have to integrate. So we need to grab this formula and apply it for this semicircle. All right, so let me write it like this. So let me check. Yeah, just Yeah, to save space, let me continue here. So b1 integral of db1, and from which point to which point? From this corner, from point A all the way to point B. Right. Another thing which I should have mentioned. All right. So why I pick direction of ds that way? Because you remember what determines direction of ds? Current, direction of current. Current flows this way. You see those arrows, right? So that's why I pick direction of ds that way. I should have mentioned a few minutes ago, but anyway, better late than never. Okay, and from integration from point A to point B. Right, and now let me rewrite all this mass. A from A to B, mu naught over 4 pi, then I, and now I will put the sign of absolute value, ds1 cross r, divided by r squared. Why I put this sign of absolute value? Because we know the direction. Direction is determined by this cross product, right? So now I just need to look at the absolute value, right? I'm just trying to find magnitude, and that's why I didn't draw a vector sign on top of b1, because it's a magnitude, right? So pretty much, what can you say about, okay, let me open my explanation box. First of all, about r. What can you say about r? R, again, recall when we introduced my Biot-Savart law, r, it's a distance from ds to the point where you want to find magnetic field. ds is here. Point where we want to find magnetic field, the center, P. So what is that r small? It's a r1 capital. And it's exactly the same if you integrate. It doesn't matter where your ds, here, here, here. It doesn't matter where your ds is. R is going to be equal to r1 capital, r capital 1. All right, so that is equal, because we are on a semicircle, r1. Then let's take care of this cross product. ds1 cross with r hat. All right. Okay, by definition, cross product, absolute value of the cross product, it's a magnitude of the first vector, ds1, then times magnitude of the second vector, it's r hat, and times, remember yesterday, sine of the angle between them. Sine of the angle. What's the angle between ds and r? Let's look at the picture. So this is tangential direction ds, r is radial direction. What's the angle between radial direction and tangential direction and radial direction? 90 degrees, right? You remember high school stuff? So this angle is 90 degrees. Okay, so it means that over here we're supposed to have sine of 90 degrees. Okay, so now sine of 90 degrees, 1, right? So as a result, we have here, and also, what's the absolute value of r hat? Usually at this point, some students struggle almost every semester, right? It's 1. It's a unit vector. We introduced this r hat in the formula as a unit vector. So absolute value is 1. So it will be equal to ds1. Okay, let me extend my explanation box, and I can close it on that side with a single line, not enough space, right? So now it means that this is r1, it's constant, mu naught constant, I constant, 4 pi constant. So all these are constants. We can take them outside of the sign of integration, right? So, all right. So it looks kind of scary, but now once we take care of everything, it's not that scary. So mu naught times I divided by 4 pi r1 squared, because this is squared, right? And r small equals r1 capital, and integral from A to B, and out of this we have only ds1 left. ds1. Okay, so now at this point you should be able to tell me what's the value of this integral. We already used this integral. Again, what's the meaning of integration? It's adding small contributions, small pieces of ds. So if you start adding ds1 small over here, I don't know, 1 micrometers, plus small ds, plus small ds, plus, and you keep adding these small ds's until you get to point B. If you add small ds's from point A to point B, of course, what you're going to get? Half of this semicircle. Okay, half of the length of this semicircle, right? It's a half of the circumference. So circumference is 2 pi r, but in this case, half of that, so it will be pi r1 capital, right? So it's just a half of the circumference. So let me write, so it will be equal to pi r1. 2 pi r circumference, this is only pi r. Okay, immediately, I don't want to rewrite, look, pi over here in the denominator, pi is in the numerator, goes, and we have r1 here, and here we have two r1s, r1 squared. So we can cancel them, right? See that? Because some students in the past asking, so how come that I cancel? This is in the denominator, is the numerator, and those are in the denominator, right? So as a result, we're getting the answer for B1 absolute value. So it's a mu naught I divided by 4 times R1. So that's magnitude of magnetic field B1 created by this semicircle at point P. So we know direction, we know magnitude. So actually now let's combine them. Right? Let's combine them. So I can write, so B1 vector equals this, mu naught times I divided by 4 times R1, and in the positive z direction. Actually I can write, emphasize, plus z. But of course, don't forget to put brackets. If you don't put the brackets, it looks like you're adding some number with the vector z hat. No, it doesn't make sense. You have to put brackets, right? So let me frame it, because yeah, it's not the final result, but important preliminary. So we will get to this at some point. Now, next step. Next step. Okay, guys, so far so good. Again, so what we just apply? We apply right-hand rule to find the direction. And then magnitude, we just integrate it. And again, most of the stuff is just constant. Right? And then carefully we open up the and look at the absolute value of the cross product. Again, just the properties of the cross product. Right? So now let me put the next bullet right over here. So that was B1. Now what about B2? It's a magnetic field created by this larger semicircle. And I'm going to apply exactly the same steps. First magnitude and then, no, first direction and then magnitude. So let me first start with direction, right? And again, direction is in ds2 cross r hat. Again, let's draw. In order to apply right-hand rule, we need to draw. We have to have a clear picture. Okay, ds2. Again, it will be over here on the largest semicircle, and direction of ds is determined by the direction of the current. So this is ds2, current that way. So that's why I align ds that way. Then r, you know what, I use my ruler. So this will be r, right? This will be our, let me write it here. This distance r, right? And r hat. You know what? I should have used different color for r hat, maybe blue. Right. So this will be r hat for the second. Again, from the section ds to the point where we want to know the magnetic field, the value of the magnetic field, right? Okay, so right-hand rule, number one, again, ds cross r. So now I have to first align my hand along the first vector in the cross product ds, so like that. Okay, just the hand, not the arm, right? Then, of course, I need to orient it. So, of course, I have to orient it like this with my palm down. So in that case, you see direction of R that way. So if I position my hand like this, I can bend my fingers in the direction of R hat, right? Because if I position like this, no way, my fingers can be bent up, and that is the opposite direction to R. So it's like this. And then my outstretched thumb gives me direction of the cross product. So which is out of the board towards you, which is negative z direction. Positive z direction I picked into the board. Right? So now I can write, you see, very similar. So as a result, let me put this and write, so B2 equals to the absolute value of B2 and in a minus z hat direction. Okay, out. I can write even out of board, of the board, but let me write out of board. So now we know direction. And again, it doesn't matter when you start integrating this, like over here, right? Directions are going to be exactly the same. If your ds2 over here, still magnetic field will be into the, out of the board, out of the board. Here, the same direction, here, here, and here, here. All those ds's, when you're going to integrate, are going to give you exactly the same direction of the magnetic field. So that's why we immediately jump to the conclusion that net B2 is going to be, direction of the net B2 is going to be out of the board, negative z direction. So now, next, magnitude. Magnitude. The same, similar integral I have to write. So it will be B2 equals integral of dB2. And now from which point to which point? First, we are here at point C, and then we are at point D. So from C to D, right? And again, I will just rewrite that ugly construction from C to D. Again, mu naught over 4 pi, then current. And then, again, I will put the absolute value sign, because now I know the direction. Now I just want to know the magnitude. So ds2 cross r hat, absolute value divided by r squared. And again, I want to open a similar explanation box in order to explain. So r from here, from ds to the point P, so which is equal to r2 capital, r capital 2. R small equals to r capital 2, and this cross product again is going to be is going to give us exactly the same. So this angle again is 90 degrees. So I can write that absolute value of ds2 cross r hat is going to give us just ds2. Similar. Okay, I will just write similar. Actually, not similar, pretty much exactly the same. You just need to rewrite it. Right. Okay, let me close this explanation box. And now, as a result, again, like here, all this ugly construction, mu naught 4 pi r squared I, again, it can be taken outside of the sign of integration, because those are just constants. So let me rewrite. So it will be mu naught I divided by 4 pi r 2 squared. Yeah. And integral from C to D, ds2. Extremely similar, right? And again, the same question. What is this? Again, strictly speaking, it's a calculus 3. In order to take this integral, you need to sweat a little bit, right? But you will do it in calculus 3. Here we just use high school knowledge. Again, it's a half a circumference, so it means that it's a pi r2. So again, pi gets cancelled. Okay, pi's get cancelled. 1r2 gets cancelled. And as a result, we're getting the answer very similar. You could have probably written it immediately because the situation is very similar. So by knowing this result, you can write immediately the result for the second part. So it will be mu naught I divided by 4r2. Right, so that's the magnitude. And now again, let me combine direction with the magnitude and write B2 in a similar way, in a vector form. So B2 now as a vector, it will be mu naught times I divided by 4R2 and in minus Z hat direction. I just combine this magnitude, right? So substitute instead of B2 this construction and minus Z direction. Okay, let me frame it. Because again, it's not the final result, but very important preliminary result. Now what left? We done this now B3 and B4. Right. So now B sub 3. Oops. Right. So let's see. Usually I started with direction and then magnitude, but in a few minutes you will see why now I'm not comfortable starting with direction. I need to start with magnitude immediately. You will see why. Right, so let's start with magnitude. Okay, I will just abbreviate magn, you understand. All right, so let me write the similar integral, but now for B3. So it will be B sub 3 equals integral from what to what? So where is my third section? Third here. From B to C. So this is B, this is C, this is section 3. So from B to C, and the same Biot-Savart law mu naught I divided by 4 pi, right? And then absolute value of ds3 crossed with r hat divided by r squared. Okay, so I just rewrote Biot-Savart law. Okay, and now let's look at this cross product. Again, absolute value of this cross product, like over here I've done, right? So, and again, let's draw it. Everything must be in front of our eyes. So ds3, direction of ds is determined by the direction of current. So it means that, okay, let me remove this vector. So this will be our ds sub 3, right? Agree? Direct current flows that way, and that direction of the current determines direction of the section ds. So I drew ds3. Then what's the direction of r hat? Like everywhere else, it's from the section to the point in question, from the section to the point where we want to find the value of the magnetic field. So here it should be the same, from ds, because that's how we wrote down Biot-Savart law. From the ds to the point where we want to know the value of the magnetic field. So it means that from ds to this point. So I can draw my r hat. Too much of blue over here. So that is my, will be r hat. You see? From this section towards point P. Right? So now you see these two vectors are anti-parallel to each other. They're in the opposite direction. ds that way, r that way, r hat. So cross product of two anti-parallel vectors. What's the value? Okay, let me write that. I will probably write in my explanation box. So it's ds3 times r, okay, absolute value of r hat. Then times sine of, what's the angle between two anti-parallel vectors? 180 degrees, pi. Sine of pi. Pretty much I'm just writing down this, opening up this absolute value of the cross product. Sine of pi. What's sine of pi? 0. Sine of pi is 0. So it means that okay, equals to 0. Let me close my explanation box. So since this is 0, so the whole integral is 0. So there wouldn't be any contribution to the net magnetic field from this section 3. So that's why I couldn't start analyzing direction, because a zero vector doesn't have a direction, right? So that's why I had to start with magnitude, justifies that it's 0, and dump just this term. So I can write so that B3 equals to 0. Okay, let me frame it again with blue, because again it's an important component but not the final. So B3 is 0. And of course now you can guess what will be the contribution from B4. We still have a few minutes. Let me finish it, because yeah, you will have to do something similar in your homework. Again, it's sort of lengthy, but each step you're familiar with each of these steps. We've done it already several times, right? Definition of cross product, how to apply them, and so on, right? So now fourth section. Now I will do it a little bit faster. So B4, and again magnitude. So B4 equals to integral from now from what D to A, from D to A, and the same mu naught times I divided by 4 pi, and absolute value of ds4 crossed with r hat divided by r squared. And again, let's draw ds and r hat, because everything around those, we're dancing around those vectors. So let me remove this vector, right? So ds, okay, again, ds is in the direction of the current, ds4, right? And then what's the direction of r hat? It's still from ds to the point in question, from ds to the point in question, from ds to the point in question. So the same here. ds is here, and from ds to the point in question. So this will be our r hat, right? You see, r hat. It's a little bit crowded. You know what? Let me erase this point A to close. And I will probably draw it here, write it here, A. So you see ds that way, r hat also that way. They are parallel. Again, cross product of any two parallel vectors 0, because angle between them is 0. Sine of 0 degrees is 0. Okay, let me hold you for extra 2 minutes, right? So let me write that down over here. So so it's equal ds4 times absolute value of r hat times sine of 0 degrees. So it is 0, right? So the whole thing equals to 0. So since this term, I mean, this factor is 0, right? It's on the picture. Sine of 0 degrees is 0. So as a result, I can write so B4 equals 0. And of course, I'm framing all these preliminary ingredients with blue, right? So it means that this also 0 contribution. Right? So now we just need to add all these contributions, B1, B2, B3, and B4. So basically we're back to net magnetic field, and the problem is solved. So now I can write so B net equals to B1 mu naught times I divided by 4R1 in a z hat direction. So it's just B1. I just rewrote it. Now I need to rewrite B2. So mu naught times I divided by 4R2, and that is in the minus z hat direction. And 0 and 0. Awesome, right? So now it looks great. So now we can factor out a few things, and the problem is solved. You know what? Let me write z in front to show the direction. And it will be in the positive z direction because this contribution is definitely stronger. This contribution is stronger. R1 is smaller, so contribution is larger. And I can factor out mu naught times I divided by 4. And what will be inside? It's 1 over R1 minus 1 over R2. Let me check. Yeah, it sounds correct. Yeah. Okay, so you can plug numbers. Again, don't forget to convert to meters. So this must be in meters. Okay, if you plug, calculate, you will end up with, let me rewrite from my notes. So it will be 7.9 times 10 to the power minus 5. Direction z hat and units of Tesla. You know, it reminds me the answer from the previous problem. Let me compare. No. In the previous problem, which I erased, we had 6.7, but 10 to the power of minus 5. So it's similar to the magnetic field strength near the surface of the Earth, right? 10 to the power of minus 5, right? So that's the problem. Again, it's kind of lengthy, but each of these steps which we applied, you're familiar. We just need to arrange them properly. And again, in your homework, this semicircle number 2 will be moved to infinity. Pretty much contribution from B2 will be 0. B1 contribution, so this section will be reduced to this arc length, I think, of subtended by the angle of 60 degrees. And again, this section 3 and 4, this will be over here, this will be still here, right? Contributions from 3 and 4 will be still 0. Because again, the same angle between ds and r will be either 0 or 180 degrees, right? So you will have only contribution from B1. But of course, you will have over here, when you integrate over the angle subtended by the angle of 60 degrees, it is not going to be equal to pi r. Here we had half over semicircle, but in your section, in your case, it will be a smaller section, maybe like, I don't know, maybe 1/8 of the circumference, but you can easily figure it out. Depends on which angle you have here, right? If it's a 60 degrees, then the whole semicircle, the whole circle is what, 360 degrees, right? And 60 degrees arc length, it's what? It's 1/6, right? The sixth part of the circumference, right? But you should be able to figure out. So of course here there will be a smaller contribution.